Hey guys, Buildzoid here, and today we're going to be taking a look at something that I've been wondering about for a very long time, and that something can be found on the back of this ASUS GTX 760 Direct CU2 OC. So let's take a look at the back of it, shall we? And of course, the thing that I've been wondering about for a very long time is this thing right here. Now, I haven't really been wondering about what it is. It's pretty simple, but I have been wondering about, like, what difference does it make? And so recently, I bought one of these cards on eBay and hooked it up to the oscilloscope to find out, yeah, how, like, what effect, if any, does this have on this card's power delivery? Now then, what is it? Because I still haven't told you that. Um, so this is what I would call a power bridge. The reason I would call it a power bridge is because I'm not aware of any like official name for what this is. As for what a power bridge is, it's basically like this one is just a big copper plate that connects from the vCore VRM, which lives over here, to the back of the GPU core. Now, basically, this goes in parallel with the existing internal vCore power plane of the card, and it basically just reduces the resistance of the vCore power plane by, adding more cross section effectively, because this is a very thick copper plate. So yeah, it has a very low resistance. So that's what it is. As for why is it on this GTX 760, I don't really know. ASUS could have decided that, they're not happy with how much power they're losing in the power plane of this card, and they didn't want to use like extra PCB layers to deal with that. So the solution that they came up with was this copper plate that, just sort of goes onto the back of the card, and you get basically more power plane cross section without actually having to add any more PCB layers. Because I'm assuming that there just isn't any more space for a wider vCore power plane in the board. And or they just decided that this would be a really good marketing stunt, right? Like it could actually be that they decided that they do want to improve, the power like. So I don't know how much of it this is like a practical design choice versus how much of it is a marketing choice. This was featured not just on this GTX 760. I think they also did a GTX 960 with this, maybe a 970. There's a bunch of 10 series cards that do have the pads, but don't have these power bridges installed. So like the padding for the connection is present on a bunch of ASUS 10 series cards, but the actual power bridge itself was never installed. So they eventually stopped doing this. But interestingly enough, say a 980 Ti Strix, which pulls a lot more current, or even like a 780 Ti from ASUS, like those are both cards that pull way more current than a GTX 760 does. Those don't feature a power bridge. So I'm assuming the main reason that they put this on this card is because this also has a really low layer count in the PCB. And maybe it is just a marketing stunt, though. Yeah, I like not too certain about that. Then again, like I don't know how it compares to other GTX 760s. And now that I've said that, that opens up some horrifying possibilities for questionable GPU purchasing decisions, doesn't it? Because, yeah, like, I know what impact the power bridge has on this GTX 760, but, like, is this card just, like, especially bad in terms of its own internal power plane, or are all 760s like that? I don't know, because this is the only one I've measured. But anyway, so what kind of effects could we expect from this? Like, mainly, I would expect this to reduce the power losses in the power plane, right? Because this effectively just reduces the resistance between the vCore VRM and the GPU core. As for voltage regulation, I wouldn't really expect it to achieve anything based on my past experiences with DIY power bridges, because I've been doing modifications to cards inspired by the ASUS power bridge for a very long time now. And one thing that's always kind of frustrated me about those modifications is that while they would pretty consistently reduce the power losses in the power plane, because it's not really that complicated. If you have a lower resistance, there's less power losses in the power plane. Like, that's just how that works. But the thing that I've been kind of annoyed with is that I was really hoping it would deliver some kind of like improvement in terms of voltage regulation, like less undershoot, because the impedance of the power plane would be lower, but in practice, I've never actually measured a improvement in voltage regulation due to a power bridge. So I was wondering, is it just because my DIY power bridges are bad, or is this just like power bridges don't actually improve voltage regulation, they just reduce the power losses in the power plane. So it's a yeah, that's the reasons I wanted to measure one of these for ages, is like this is the like proper professional implementation of a power bridge. So, is it just my power bridges that suck, or is this just like power bridges just don't do anything for voltage regulation? So anyway, um, yeah, that's what I've been wondering about, and that's what I went ahead and measured recently. Now then, yeah, here you can see the power bridge from another angle. As you can see, it's a copper plate. It's very thick, which was kind of surprising to me. I don't know what I expected the thickness to be, but yeah, it is a substantial piece of copper. Um, and then here you can see it without the sticker. It's not it like the reason it's so yellow instead of like copper colored is because it's actually like it's an old card and it's very oxidized. So yeah, that's not like I think if you got the card brand new from the factory, this would have been like this color, not this yellow color. Because yeah, this does seem to just be like an oxide layer that's built up over the years. Anyway, here you can see where I decided to hook up the oscilloscope. So I'm just running coax all the way to the card. This is my preferred method of doing voltage measurements because it is very good at not picking up things like VRM switching noise by accident. Because, yeah, that's a really frustrating thing is if you put a probe or if you have any amount of like exposed wire and you run it like anywhere near the like switch nodes of a switching regulator, it has a tendency to end up picking up the like the actual like PWM signal from the switch node. So yeah, and using like coax basically as like all the way to the board does a really good job of avoiding that issue. Um, so yeah, anyway, as for why I chose the voltage measurement points I did, well, behind the core, it wasn't really, like, I wasn't really, like, there wasn't really too much consideration for it other than just, I want a good, like, physically robust connection. And so the polymer capacitors are the best option for that because multilayer ceramics are not exactly physically robust things. Um, so, like, soldering coax to multilayer ceramics, like, I have done it when desperate, but I tend to avoid it because if you, like, if you pull on the coax badly, then it'll, like, break the multilayer ceramic capacitor. So I don't really want to do that if I can avoid it. And so here, yeah, I soldered it to this aluminum polymer capacitor because, well, there's no way I was going to be connecting it to this one or this one. Right? There just isn't enough space to get the soldering iron in there. So I went with this one. As for the capacitor for the VCore VRM, I guess I could have used the unpopulated pads over here, but it doesn't really actually make a difference because the main thing, like, I don't actually care about like what voltage, like what the peak-to-peak measurement at the VRM looks like because like the core is over here. So like if we have a lot of peak to peak over at the VRM, that doesn't really matter that much because it's not like the core can't see that, right? So really, this is more for getting an average voltage measurement from the VRM area, which is the point of that probe. So yeah, that was just, and it was just kind of convenient to hook it up to the capacitor, though. I did want to hook it up relatively close to the power bridge because I didn't really want to be measuring like the too much of the effects of the power plane itself on the card, right? So yeah, so that's why I chose the measurement points that I did. Like this one's just, there wasn't really a better place to connect the coax, and this one was just, I wanted it to be kind of near to the power bridge. So, yeah, as for, oh, and the last thing to mention is that I am using a 50 ohm termination at the oscilloscope. Because, yeah, running coax straight into a 1 meg ohm impedance, like input impedance oscilloscope tends to cause a mess because especially if you're measuring like very fast transients, those will actually just end up reflecting a bunch, and then your measurement is basically useless. So I do have a 50 ohm termination at the oscilloscope for this. Now then, here you can see the card with the power bridge removed, right? And the experiment here was literally just like connect coax to card, measure it, remove the power bridge, measure it again, see what the difference is. So not exactly very complex. So here you can see what it looks like when I remove the power bridge. Also here you can see that the power bridge actually like goes over a bunch of PCIe lanes, which kind of nice to have a very like obvious visual indication of what this is bridging across. Though I will say, like, this style of like PCIe lanes coming into the GPU core, like this, is very typical of low-end NVIDIA cards. Like, I think even a lot of GTX 970s have the PCIe coming in through this area, and actually even on modern cards, this is very common. Like, yeah, it is very, very normal for the PCIe lanes to come into the core through this area. So it's honestly, I mean, I don't know if it's that weird that the power bridge has like that you don't see the power bridges anymore from ASUS. But yeah, like here, like it visually makes a lot of sense, right? Because it's like, oh, we've got PCIe lanes on the top layer, so you can't run the vCore power plane there, so you can just go over it with this great big copper plate. But yeah, anyway. Also, here's the power bridge when I desoldered it. So that's all it is. It really is just a copper plate with some tabs bent off of it. Also, if you're wondering how I desoldered it, I do have a soldering iron that's just powerful enough to heat the entire plate up to lead-free soldering temperatures. So that's what I did. I literally just, I have like a 6.6 millimeter chisel tip. So I just sat the soldering iron at the middle of the plate until the entire thing just came off. Alternatively, I could have used hot air, but I didn't want to use hot air for this because hot air is very like inaccurate in terms of how much stuff you're heating up. Whereas with the soldering iron, I can just heat the copper plate directly. So yeah. Anyway, also the soldering iron that I use, I think has a peak power of 150 watts. And the reason I bring that up is if you use something like a 30-watt soldering iron, I imagine it would either not achieve anything or it would actually get stuck to the copper plate. One of the two. So, yeah, it helps having a soldering iron that has basically the same TDP as the entire GPU. Anyway, let's take a look at the measurements. So, here we have the measurements from a Rigol HDO 1104. I am using the full 100 megahertz bandwidth on both of the channels. Channel 3, so the pink one, that's from the VRM, right? So that's, where is it? Yeah, so the pink line is this probe, right? So that's the pink, and the yellow is, of course, the core. So that's this probe. That one's yellow, that one's pink. So anyway, the first set of, I mean, actually, if you just look at these, it should be pretty obvious which which oscilloscope captures have the power bridge installed and which ones don't. Because there's like a pretty big gap between the yellow and the pink line on some of these captures and not on the others. As for what test I was running, this is all Firestrike Graphics Test 1. So this is at the end of the test, and I did run 2 passes each time, so we have 349 samples into the like averaged measurements. And the reason I've done 2 passes is just to make sure that there isn't some like weird one-off like undershoot event, which, yeah, you can see that, you know, pass 1 we get a minimum at like worst case, like the worst undershoot that I measured was 1.0485 volts. And then on the second pass, it was 1.0485 volts. How very convenient. So yeah, the runs are very, or well, I shouldn't say very because this is just 2 runs, but relatively reproducible and like good enough for my purposes here, as far as I'm concerned. So anyway, I guess we're going to start with the like average voltage differences. Also, you'll notice that I did try my best to get the voltage offsets of like the vertical. Wait, is it the vertical? Yeah, the vertical offset of each of the channels matched up. It's not exactly matched. The pink channel is actually at 1.099 rather than 1.1, but close enough. So yeah, plus we're just using the measurements anyway, so it doesn't actually matter if visually they are lined up perfectly, but I thought it would be nice if we could actually just have them like overlaid on top of each other pretty closely. Anyway, so um, oh, also I should mention that I didn't let the card get up to equilibrium temperature, as in I didn't let the card sit there running Fire Strike for like an hour before taking the measurements, mostly because I'm lazy, but the reason I bring this up is because copper has more like the electrical resistance of copper increases with temperature. So if you have a card, and the PCB is at 20 degrees Celsius, which it wouldn't be by the end of a Fire Strike run, but when you first start the test, if the PCB is at say 20 degrees, and like that's gonna change how much voltage drop there is in that power plane compared to if the PCB is at say 90 degrees, right? I don't know where the equilibrium temperature for the power plane on this card is. I also don't really care because I'm not going to be running the card on sustained loads, but that would potentially increase the differences between the like no power bridge versus with power bridge measurements that I've taken, because the power bridge I would reduce the power, like it would lower the equilibrium temperature, right? Because there'd be lower power losses in the power plane, so the power plane would end up at a lower temperature. That lower temperature would mean the power plane resistance would be lower. So you have like this like stacking effect if I actually ran the test for longer, but I wanted just a very quick like, so how much of a difference does this really make? So this is kind of like a worst case scenario for the power bridge, because if I did let it heat up, it would probably be more effective at reducing the power losses in the power plane than with my very quick test of I ran Fire Strike once, I ran Fire Strike twice, and even in that like short, so like there was a like I didn't let the card cool all the way back down to room temperature, but I didn't bother to let the card get up to like equilibrium. Um, so that is worth noting. That yeah, like if I ran the test longer, we would potentially see bigger differences between the stock configuration and the configuration without the power bridge. But anyway, so let's just talk about the voltage drop between the vCore VRM and the back of the GPU core. And so at stock, so with the power bridge installed, at the end of the Fire Strike run, the average voltage was like 1.1729 volts or 1.1731 volts, which functionally the same thing as far as I'm concerned. We'll call it 1.173. And then the voltage at the VRM was like the average voltage by the end of the run was 1.1944 versus second run was 1.948. So we'll call that like 1.94, I guess, right? Yeah, we'll call it 1.94, something like that. So basically between the so we'll go back to this photo. So basically between our two measurement points here, we have a voltage drop of about 22 millivolts, which is very low. Yeah, that is actually just very low. So that's neat. Potentially, we might have seen a bigger voltage drop if I measured from here. But I wanted to measure the effect of the power bridge, so that doesn't really, like, if I measured from here, because the thing is, like, I don't know what the internal, because the card does have an internal vCore power plane, right? So I don't know what the internal vCore power plane shape is. For all I know, it might do something like this to sort of, like, it might be something like this so that it avoids the PCIe lanes that are coming in through here. So maybe this would actually not be that, like, the voltage over here wouldn't be that different from the voltage over there, but I don't know. I didn't, I guess I could have used a third channel to measure like the far end of the vCore VRM, but I am interested, but not that interested. So anyway, so with the power bridge installed, the card has about a 22 millivolt voltage drop across the like between the core and the vCore VRM, and that is quite low. Yeah, from my, like, I've measured a few cards, and I don't think I've measured anything that low before. So, anyway, or is it? Yeah, no, like, I shouldn't have got, it's low. It's pretty low. off the top of my head, it's pretty low. I unfortunately don't usually measure this for every card because it's not really that important usually. Like, yeah, but anyway, so about 22 millivolts in the stock configuration. Now, with the power bridge removed, the average voltage didn't really change. It did actually drop a little bit, but it didn't like significantly change. And I'm guessing the reason why it slightly dropped is because the measurement point that I'm using is not the so the voltage regulator on the card actually has a direct connection to a like voltage measurement point on the actual package of the GPU. So in the like the pinout of the GPU core, there's an actual pin for like core voltage measurement. And that's what the voltage regulator is regulating against. It's not regulating against wherever the hell my coax is hooked up, right? So the core voltage regulator actually has no idea what the voltage over here is. So I'm guessing what's going on is that the average voltage is a bit lower because the voltage regulator is regulating against the core, and there's basically some voltage drop from the back of the card to the actual silicon on the front of the card, right? So the average voltage on the back of the card has dropped by a fraction of a millivolt. So now I feel like maybe I'm just wrong because that's so small that that could actually just be. Well, it is. See, I'd like to say it's like, oh, it's just measurement tolerance, but no, we get that twice. Right? That is consistently about a millivolt or two lower. So that might be a real effect. Yeah, having an oscilloscope that measures voltages to 4 digits is wild. To 4 decimal point. Actually, yeah, to 4 decimal points is a bit much because this is actually just like 1 millivolt of difference. So it might be repeatable, but I'm not 100% certain on that. But if that is actually going on, then it's probably because the voltage measurement point is actually on the, like, the voltage regulator regulates against the silicon, not against the back of the card. And so, you know, now that it's a bit harder for power to basically get from the vCore VRM to the back of the back of the core is at a slightly lower voltage than it used to be. Anyway, but yeah, so we get a very small reduction in average voltage. That honestly, if like it's a millivolt, so yeah. And then we get a really big increase in the average voltage at the output of the VRM, which is what you'd expect when your power plane resistance, you know, suddenly drastically increases. And so actually with the power bridge, so run 1, right, we get 1.172 versus 1.234, and run 2 we get 1.172 again against 1.235. And that's about 62, 63 millivolts. So go back here in this configuration, right? Going from here to here, we have a voltage drop of 63 millivolts. Which basically means that let's say you had 100 amps going from the VRM to the GPU core. This would produce, that would be like 6.3 watts of heat. That would be getting dissipated entirely in the power plane. And that's kind of the sort of the like thing that, yeah, like that 6.3 watts is entirely in the power plane of the card now because there's no power bridge, right? Whereas with the power bridge, right, where I measured 22 millivolts of voltage drop from, you know, here to there, if we had 100 amps flowing to the core from the vCore VRM, which I think in the stock configuration the card doesn't pull that much power, but when you start overclocking, you can get these cards to pull quite a bit. Though at the same time, if the card is pulling more current, then the voltage drop is obviously going to increase. So you get the idea. But this is the 100 amps here is for illustrative purposes only. Yeah, though it's probably not that far off what a GTX 760 pulls because it runs at like 1.1 something volts, right? So 100 times 1.2 volts It doesn't even run at 1.2 volts, like 1.17, like we're getting like 1.17 on the core, so that would be 100 and actually at the VRM we're getting 1.2-ish. So we'll call that 120 watts. Then some kind of power losses in the VRM, let's say 10 watts or something. Let's say 12. Yeah, let's say 12. So that would be 132 watts. Add the memory to that, and like I think GTX 760s are somewhere around 150 watts, something like that. So actually 100 amps across the power plane probably isn't that far off of what it is in reality. Um, but anyway, so in this scenario, we'd get only 2.2 watts of power loss across the uh, power delivery network to the core, right? And the crazy thing is, those 2.2 watts, like some of that power would be getting dissipated in the actual power bridge itself, right? So that wouldn't be heat being produced in the PCB. That would be heat being produced in this plate, and this plate obviously, like on, probably has a easy like is more cooling friendly than the power plane itself. Where you could kind of a silly idea that you could do is like stick heat sinks onto the onto the power bridge. Not that I, which would probably produce measurable effects under like sustained high load scenarios. That you could actually measure a benefit from strapping heat sinks to the power bridge, to make sure that the power bridge is as cool as possible. But yeah, so honestly, like so in terms of like the improvement going from like no power bridge to with power bridge, we're talking like saving about 4 watts in the power delivery to the core, um, which is something, I guess. It's not nothing. It is measurable, but at the same time, I can kind of see why ASUS decided to stop doing power bridges at some point because yeah, this isn't doing much. Um, Yeah, especially and also if you consider that by the like because the last time Asus was still putting the actual like pads for power bridges onto their PCBs, that was 10 series, right? And 10 series GPUs basically don't pull any power at all. So it kind of makes sense that by 10 series Asus just kind of gave up on this idea because well, the current draw probably wasn't high enough to justify the extra expense. Not that I think this probably isn't very expensive, but um yeah, I can kind of understand why they ditched it. Anyway, now, so it does improve the power losses in the power plane. Um, Also, if I had let the no power bridge setup run to like equilibrium temperature, I think it would have, like, we would have seen an even higher voltage drop at some point, right? Because, like, we're dissipating like three, it's not literally 3 times, but something like significantly more power is being dissipated in the like power plane of the or power planes because it's a multi-layer PCB. There probably isn't a like just one V-core power plane. Maybe there is. Maybe it's like a 4-layer PCB. I don't know how many layers this board has, um, but yeah. So I don't know. Like, so we're going from like like the thing is like I don't have measurements for the entire power plane, so it's not really correct to say that oh the entire like from the VRM to the core, it's definitely just 2.2 watts because I don't know, maybe there's going to be some power, like potentially somewhat a higher voltage drop from like over here to here. So there's going to be like a gradient of voltages across the entire like V core to V, like core to VRM connection. Right. So the fact that like across this section of it we're seeing 22 millivolts doesn't automatically mean that like this isn't maybe another 10 millivolts higher. And I also don't know how much current is flowing through each part of it, so it gets complicated. But this is a pretty substantial increase in voltage drop. So we'll say 3 times based on my measurements, but my measurements are not all encompassing, so there's some error in that probably. But anyway, so yeah, if we ran this to like equilibrium, right? This is now putting out like 3 times more heat, and all of that heat is now concentrated in the PCB itself, right? Because the power bridge isn't there anymore. So I'm thinking like, yeah, if I ran the no power bridge configuration for extended periods of time, as in if I just let it get up to like, you know, equilibrium temperature, um, it would have potentially had an even bigger voltage drop across it. And actually, one of the reasons I decided not to try to run it to equilibrium was I wasn't entirely certain if the PCB of this card is actually designed to require the power bridge. Because theoretically, you could have a PCB where the internal power plane is so thin that if you ran it for like extended periods of time, it would just keep increasing in operating temperature indefinitely. Like the PCB would never be able, which is probably pretty unlikely, but like you could have the internal power plane end up at some insanity temperature of like over 100 degrees or something. And actually, there was a Z590 or Z490 motherboard where I measured basically that exact situation where the VRM temperature was fine, and the temperature of the PCB a couple millimeters away from the CPU socket was sky high because the board was like a 6-layer PCB, and all of the current trying to squeeze into the CPU socket was basically just heating up the power plane right before the CPU socket, which is where it gets narrowest. Also, I guess the pins in the socket probably produce some heat as well. So that was like, so you had this really weird situation where it's like, yeah, the actual like MOSFETs, the active components, the switching components were running cooler than the board like way out in front of them. And so I didn't really want to test if like this PCB can actually like, because I don't know. Maybe it probably does. It's probably actually like I would guess that this is probably very similar to a reference GTX 760. Actually, no, because this is an ASUS card. ASUS likes to do rather heavily customized PCBs basically as much as possible. Like a lot of other manufacturers will basically take a reference NVIDIA card and then just slightly shuffle some things around. But ASUS likes to make cards that look very distinctly different from reference NVIDIA cards. So yeah, I don't know. I didn't really want to. I didn't really want to see if like the PCB ends up at some insanely high temperature if I just run it with no power bridge for a long time. Um, Also, it would have just taken forever, and I like I do wonder about the power bridge effectiveness, but I don't wonder that much. So anyway, the other thing I wondered about is, does this have any impact on voltage regulation? And the answer is no. No, it does not. Or at least it doesn't have any impact on voltage regulation that I care about, because if we look at the max measurements, actually, nah, it doesn't. Because, like, technically, like, yeah, you might be like, oh, the average overshoot was 1.299 volts versus 1.301 volts. And it's like, yeah, so that's like 2 millivolts. So that's not a difference. And that's across both runs, right? Like here we have a max of, actually this is a, no, that's absolute max. Here we have a 1.3 versus oh, look, actually here the average overshoot is actually slightly lower than in the previous test. So yeah, the maximum voltage did not change. The overshoot is the same, regardless of if the power bridge is there or if it isn't. Though I will say one thing I find interesting about the card when the power bridge is installed is that we get overshoot spikes behind the core that are taller than the peak voltage at the VRM. Um, yeah, which is super weird because I would have always figured that you'd get the highest voltage directly at the VRM itself rather than at the core. Because as far as I know, the overshoot is caused by the excess energy stored in the inductors having nowhere to go. But by the looks of things, here we seem to have some kind of like extra, like there's some like extra kick from like the power plane towards the core, or something, because yeah, like we get more peak voltage directly behind the core than we do at the VRM, which doesn't really make like sense to me within my understanding of like the overshoot comes from the inductors, and it's like, but that, like, if the overshoot comes from the inductors, why are we seeing more overshoot all the way at the actual core than at the VRM, which is like right next to than at the inductors, right? So I guess there might be some kind of like the inductance of the power plane itself is actually causing a even higher overshoot directly behind the GPU core. As you're basically, because when the core transitions from high load to low load, all of that current that was flowing through the power plane, well, it still kind of wants to keep going, probably. And that's piled on top of the current that's in the inductors. And that would probably explain why we're getting, you know, spikes on at the core that are actually taller than spikes at the VRM. Which, yeah, that's actually, like, I did not expect that. Um, so, anyway, but the actual, like, like, the overshoot level in and of itself hasn't really changed. Um, right? Though it is worth noting that when I remove the power bridge, the overshoot at the VRM is actually, like, yeah, see? Pink is now above yellow. Actually, pink is consistently above yellow. Um, so that's kind of interesting. Is like, yeah, when there's less resistance in the power plane, we actually end up with the spikes at the core being taller than the spikes at the VRM. So that's an interesting effect. Now, undershoot, which is the part that I actually care about, because this right here is what causes the GPU core to crash when you're running a benchmark at very high clocks. Or just generally, if you're overclocking, you want as little overshoot as possible, right? So, did the undershoot, I mean, you want as little undershoot as possible. The overshoot is kind of like, it's obviously not great if the overshoot is super high, but it doesn't cause blue screens, so I don't particularly care about it. Anyway, the undershoot, on the other hand, so run one with the bridge, we minimum is like 1.0485, average is 1.0675. Without the bridge, we're looking at 1.066, so slightly worse, and then the worst undershoot that I measured was 1.0485, so exactly the same. And actually, 1.0675 and 1.066, 1.066 is only 1.5 millivolts apart. So functionally the same. And if we look over here, oh, look, 1.066, 1.0527. So this is actually slightly better than either of the runs with the power bridge installed. And yeah, though the average here is actually better than the average for either of these by 2 millivolts, or actually, no, that's like 3 millivolts. So, does the power bridge improve voltage regulation? No, it doesn't. It just doesn't whatsoever. So now I don't have to feel bad about all of my DIY power bridges basically behaving the same, because that's been my experience. Like, I've had, like, I've done this with multiple cards as, like, like, just trying to do anything to get the voltage regulation to be better. And so one of the things that I've messed with was just like adding like really thick copper wires or copper plates going all the way from the like vCore VRM to the core. And very consistently, the only effect that I've ever managed to measure is that it reduces the power losses in the power plane. I've never seen it improve the voltage regulation. And well, evidently it's not supposed to, because even this, like, ASUS implementation, which probably has significantly more engineering behind it, or at least you'd hope it has more engineering behind it than my DIY attempts of just slap some copper somewhere. Yeah, this doesn't do anything for voltage regulation. Like, it just doesn't. The voltage regulation hasn't changed whatsoever. Like, the only reason we can see a difference is because the HDO 1104 is a 10-bit oscilloscope, and so it measures to just like 4 decimals, which is like differences of less than 5 millivolts are not relevant. And even 5 millivolts, I'd say, is like, okay, that's probably more dependent on like measurement methodology and like how many runs you've done than it is an actual noteworthy effect. So yeah, this really, like, power bridges evidently do not do anything for voltage regulation, which is quite interesting. Though, actually, there is an exception to that. And that exception is if you're e-powering a GPU. So if you replace the VRM with a different VRM, and the reason that actually sees a difference in voltage regulation if you add a power bridge is not because of some inherent property of the power bridge, but it's because when you're doing external VRMs, or when you're replacing the VRM with an e-power, the e-power, if you don't reference it to the GPU core, the e-power regulates against its own output. So if there's a lot of resistance between the output of the e-power and the back of the GPU core, and and you have to consider that, like, so there's the resistance of the you have the resistance from the output to like the connection you made, And then you have also the resistance of the existing power plane in the board that you just e-powered, right? So those two resistances get added up, and that's going to like mean that there's going to be like the e-power is regulating the voltage against its own output, so the voltage at the core is going to basically be offset by that resistance depending on the current flowing through the resistance between the e-power and the core. So in that scenario, adding a power bridge is going to change the resistance, which is going to change the like the voltage regulation at the core, because there's like less resistance between where the e-power is regulating against and the core. But if you just reference the e-power to the actual core, you basically end up in the same situation that you end up with a stock VRM, because the stock VRM of the GPU regulates against the core, which is why it doesn't really care if the power plane has like 3 times more resistance in it. It just kind of compensates for that, because the VRM, right, like the voltage regulator doesn't, it doesn't know what the voltage over here is. It doesn't really care. It just knows I'm supposed to reach, I think for this card it was like 1.15 or something volts, right? This is my target voltage. I will increase the PWM signal at the inductors until, I'll increase the PWM signal until this voltage is achieved, right? So how much resistance is between these 2 points kind of doesn't really matter to the voltage regulator. Now, there is like, if the resistance is high enough, then at some point it does actually become a problem, but not inherent, like small amounts of resistance is just like, yeah, the voltage regulator actually just doesn't care. So yeah, that's why the power bridge really just doesn't do anything for voltage regulation. It just reduces the power losses in the power plane. So nice to have that measured, I guess. And now I also took some like zoomed in captures, because obviously all of these captures, I forgot to mention it, but these are at 5 milliseconds per division, right? That's my preferred way of measuring things, so that I get a lot of spikes onto the screen at the same time. But anyway, here we have some zoomed in captures, and yeah, like this, right? Like here you can very clearly see that like we have a load release overshoot, and at the GPU core, it is like a lot higher than it is at the VRM, which is super interesting. So I'm guessing like this extra voltage is like coming from the inductance of the power plane or something, because if it was coming from the inductors, you would expect the pink line to be taller, right? Or at least I'd expect the pink line to be taller. Anyway, you might also notice that the pink line, for whatever reason, is like thicker than the yellow line. And I think the reason for that is that if you look at, actually, no, you can't look at it, but the way the VRM on this card is designed, there is basically no multilayer ceramic capacitors directly at the output of the VRM. Like all of the multilayer ceramic capacitors on this card are, like all the V-core multilayer ceramic capacitors, I should say, are here. Or right here. There's like, yeah, there's nothing directly at the output of the VRM. There's like some over here that are for V-core, but the bulk of the like high frequency filtering is directly behind the core. And then right at the output, you just have some through-hole aluminum polymers, which have a ton of equivalent series inductance. So they really don't filter out like high frequency switching noise. Basically at all, which is probably why we see the like peak to peak, like the like in this like relatively steady state looking region right over here. Why this is like fatter than this is probably because there's no multilayer ceramics directly at the VRM. So yeah. But I do find it really interesting that like the overshoot is actually worse at the core than it is at the VRM, because I would have never expected that. And I guess like my guess for why that is just the inductance of the power plane itself, because like I don't like admit, like I'm not an engineer, so I could be completely wrong about this, but I'm not aware of anything else that would be causing this. So yeah, I'm gonna go with like the power plane is doing that because I don't know where else that extra voltage is coming from. Um, anyway, with the power bridge removed, uh, there are some differences in the spikes again, but well, now the pink spikes are taller than the yellow spikes, though you can also see a slight offset in when the spikes happen, which is interesting, right? Like where the peak is. Like this peak is obviously earlier than this peak, but that could also just be down to the difference in capacitor configuration. Um, all right, so yeah, these are kind of interesting to look at, but not really useful in terms of judging how effective how effect like these are cool to look at, but there's not like a lot of like, oh, this is what like I like I'm not seeing any like useful to me information out of this is what I'm trying to say there. Which might be just because I'm too stupid to understand what I'm looking at here. Um, but yeah, like from what I find this interesting, but there's not really anything I can do about that. I mean, it's just like, well, I'm just gonna throw more capacitors directly behind the core anyway. So like, what difference does it make? Um, right? Because that's ultimately like how do you make that spike smaller? More capacitors. So that hasn't changed. Um, and this measurement right here is just like, well, we're seeing kind of the same thing, except now the pink line is offset upwards by a certain amount. So yeah. Anyway, that's it for this video. Hopefully you found it somewhat interesting, if not particularly useful. Um, but yeah, this is something I've been wondering about for a very, very long time. Is like, did this actually do anything? And the answer is, I mean, technically it would give you slightly more performance if you were riding the power limit, right? Because you're losing less power in the power plane, but like, it's like 4 watts. It's like not a like it's like most benchmarks aren't like yeah, I'd say most benchmarks literally aren't consistent enough to measure the performance impact that this would have in a power limited scenario. Unless we were, well, no, the thing is, if you have a really low power limit, then the amount of current flowing through the board is going to be really low, and the effectiveness of this is going to get reduced, right? So this is most effective when you have a lot of current flowing, and yet somehow and you're like riding the power limit. That would be when this would actually have like a performance impact. From an overclocking perspective, uh, like from like should you do this mod to your GPU perspective, this is pointless. Anyway, this video is now way longer than it ever really should have been. Um, but yeah, hopefully you found it interesting. So that's it. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video, so thank you for watching, and goodbye.